Scaling to a 1 million token context window hits a mathematical limit. Standard attention mechanisms scale quadratically, memory and compute demands violently explode. To break past this wall, engineers have to move beyond the vanilla attention architecture entirely. This chart shows DeepSeek-V4 Pro Max's benchmark performance. On the left, it matches frontier closed models in knowledge and agentic capabilities. On the right, it achieves this with 9.8 times fewer single-token flops and a 13.7 times smaller KV cache. These efficiency gains originate in a fundamental algorithmic rewrite targeting the specific computational bottlenecks of ultra-long sequences. We are going to deconstruct the three core pillars: hybrid compressed attention, manifold constrained hyperconnections, and wave-scheduled expert parallelism. DeepSeek-V4 manages its 1.6 trillion parameters through a specific set of redesigns in how data is cached, routed, and stabilized. During text generation, a model stores the hidden states of past tokens in a KV or KV cache to avoid recomputing them. At a context window of 1 million tokens, storing every single state requires a physically impossible amount of memory. The first solution is compressed sparse attention, or CSA. As tokens process, CSA mathematically groups blocks of input states, using learned compression weights to merge them into a single, dense entry. By consolidating every M tokens into one, the architecture effectively divides the total sequence length by M, drastically cutting the cache footprint. To find relevant data within that compressed sequence, DeepSeek uses a lightning indexer. A query token projects a low-rank beam to calculate index scores, selecting only the top K most relevant compressed blocks to attend to. To maximize speed, this indexing calculation is executed entirely in FP4 precision. The second half of this system is heavily compressed attention, which interleaves with the CSA layers. Here, a much larger block of tokens is compressed down into a single node. Because the compression rate is so high, heavily compressed attention skips the sparse selection step entirely. Instead, the query token applies dense attention uniformly across these heavily summarized global contexts. However, aggressive compression risks losing the immediate local dependencies between adjacent words. To prevent this, both the CSA and HCA layers retain a separate, uncompressed sliding window attention branch, specifically for the most recent tokens. By interleaving highly compressed global states, sparse indexed medium states, and dense local states, the model resolves the KV memory wall while preserving precise recall accuracy. Algorithmic compression solves the memory problem, but it exposes a new vulnerability. A 1.6 trillion parameter network will mathematically collapse if the signals degrading across its depths aren't stabilized. A standard method to scale a model's capacity without massive compute overhead is expanding the width of the residual stream using hyperconnections. But there is a flaw in this design. When you stack unconstrained transformation matrices across dozens of layers, the variance of the signal compounds, eventually leading to numerical instability. DeepSeek-V4 addresses this with manifold-constrained hyperconnections. Instead of letting the mapping matrix float freely, the architecture forces it onto the manifold of doubly stochastic matrices, a bounded topological surface known as the Birkhoff polytope. This constraint is generated dynamically using the Sinkhorn-Knopp algorithm. Rapid, iterative waves of normalization are applied across the rows and columns of the matrix until both sum exactly to 1. Mathematically, this guarantees that the spectral norm of the mapping matrix is strictly bounded by 1. It creates a non-expansive transformation. As the signal propagates through more than 60 neural network layers, its amplitude can no longer compound or blow out. This topological constraint provides the mathematical scaffolding required to reliably train an incredibly deep mixture of experts architecture. The final physical bottleneck in a mixture of experts model is the hardware interconnect bandwidth used to route tokens between GPUs. In a naive routing setup, an all-to-all dispatch phase creates a massive traffic jam. GPUs sit completely idle, waiting for token data to travel across the network before any math can be executed. DeepSeek engineered around this with a specific realization. Physical interconnect bandwidth limits do not matter if communication latency is entirely hidden beneath computation time. There is a precise mathematical threshold for this. At roughly 6,144 flops per byte, the computation takes long enough to completely mask the data transfer. To exploit this, the system uses wave scheduling. Instead of operating as a monolithic block, the experts are partitioned into small, staggered waves. As soon as Wave 1 finishes receiving tokens, its computation begins immediately. While Wave 1 computes, Wave 2 is simultaneously dispatching its tokens over the network in the background. This entire overlapping sequence is executed by a single, highly optimized, fused pipelined megakernel. By structuring computation and communication as continuous, concurrent streams, the architecture bypasses physical hardware bandwidth limits to drive the GPU cluster to maximum utilization. DeepSeek-V4 shrinks the sequence length through hybrid attention, anchors its deep layers with manifold constraints, and routes its tokens through overlapping hardware waves. But the final and most crucial step to reach its massive deployment efficiency profile requires a technique known as quantization-aware training. After the primary training phase, the massive mixture of experts' weights and the Lightning Indexer's query key paths are quantized down to FP4 precision, slashing memory requirements even further. Because the model was trained explicitly to adapt to this lower precision, it processes the FP4 data during inference with virtually zero degradation in accuracy. This chart graphs the single token inference flops across sequence lengths. The blue line tracks the DeepSeek-V4 Pro model, demonstrating how flat and low the computational load remains, even as the sequence stretches towards 1 million tokens. DeepSeek-V4 is a complete architectural redesign. By establishing a radically lower computational floor, it makes complex agentic workflows and test-time reasoning viable at a massive open-source scale.